Good morning, afternoon, or evening, gentlemen. Hope you're doing well today. Professor Shoemaker here. It's going to be the April 27th, Monday lecture for today and the quiz to follow in your D2L assignments. And today we're going to be talking about capacitor banks. Operation, installation, why do we need them, and a good bit of detail behind that in the situation of what's going on with them and their use. So I've found that, having a script ready here is definitely beneficial in the situation. I post those scripts on the D2L news. When you go into your D2L, you'll have these notes, and also there will be a quiz assigned to it from those notes with questions on it. So in the capacitor bank world, as far as electrical power systems are concerned and utilities, we're going to talk about capacitor banks and power factor. A little bit technical here in the beginning. Want to give you the technical side of it. Plus, I like to scale down and summarize something for you in case a person asks you, or you go into an interview and they ask you a technical question of, well, what's a capacitor bank used for? Why do we have them? Whatnot. A short, this is what they do, this is why. And we'll go on from that. Okay, so to start, what is a utility capacitor bank? Well, it's a bank of capacitor units rated in kVAR. We'll talk about kVAR here in a little bit. Per unit installed on a pole or pad mounted unit near inductive loads to improve system power factor. And we'll talk about that in further detail. So, get you some pictures going on here. Looking at this picture right here, what we have is a substation capacitor bank. This is going to be located inside a utility substation, and you can see the individual units. And this is what I mean by banking them together. So you can actually stack these units if you need more capacitance introduced into your circuit. This is for transmission. This, for you gentlemen, they're going to be working on the distribution side, is a typical installation. Not all are the same. Different utilities have different designs and different structure to theirs, but they all have the same essential parts and pieces going on in it. So what we have here is, of course, our stirrup, hotline clamp, high side riser to the arrestor, and the arrestor to the switch. Then we have a low side riser off the switch, and they go to these vacuum bottles. Talk a little bit about those while we're on this picture. And of course the switch is fused, and we have a unit or capacitor bank for each individual phase. So one goes to this phase, one goes to the top phase, which is out of the picture here. There it is. And then another high side riser goes into the switch fuse and then goes into this one. So we'll look at this one a little bit closer here because it's staring us right in the face. You'll notice it comes off the fuse switch and then goes into a vacuum bottle. And this is the load break part. And then that vacuum bottle goes into the capacitor bank. So it's an in. There's a vacuum switch inside here, so I can make and break load inside this vacuum bottle, and then goes into the capacitor unit. And there are 3 individual units in this bank. So 1, 2, 3 units. When I say bank, it's the full enclosure right here. And when I say units, that's the individual capacitor cell that you see inside the unit. And take note here that this handle is down. So this vacuum switch is open. That one's open. And I would suspect on the other side, that one would be also open. You notice also here, down at the bottom, there's a control box and a cabling system that goes down to what they call a control panel that's mounted down at the bottom of the pole. I'll have some pictures of that. Here, there's the control panel that's mounted down towards the bottom of the pole, so you're able to actually do things here by radio. And you'll notice this one out here at the college. I'll zoom in a little bit for you. Okay, switches, phases, low side riser to the vacuum bottle, bank, and you'll notice right here, wires coming down the pole You've got an antenna, so the SCADA radio can actually reach the control box. So you got an antenna to receive the SCADA transmission, and then the control box down at the bottom. You can manually operate the bank here at the bottom, or SCADA control. Okay. So what is kVAR? kVAR is a unit of reactive power. As you must be knowing, I just copied and pasted this here because it's a good one, but it's not really, I would say, scaled down to be able to relate to what we taught in the course and everything like that, what you need to know as a lineman. There is two different types of power. There's active power, and we'll call this resistive. When they say active power, when I turn a switch on, a light comes on, and that's a complete circuit. We've talked about that before. So it's a resistive load. When we use a light, light produces, of course, light, and it produces heat. And there's a reactive power. That's inductive. So what I have to do in reactive power, and something has to react. When I close a switch to a motor, electricity goes to the first coil in the motor. It creates a magnetic field. And that magnetic field goes across the other coils inside the motor, and then the motor turns. So that's not really a complete circuit per se as far as physical contact. This is physical contact, resistive. Complete circuit through the bulb, through the element to ground. This one has to create a magnetic field. Now the active power is the power which is consumed in the system to do some work. And for the reactive power, as we know, that most of our loads are electromechanical loads. So inductive is electromechanical, well, that motor. The input cannot be directly converted into the respective form. Well, that's resistive. I can't take a complete circuit there, close a switch, light the light bulb up. I've got to convert it first. Thereby, intermediately converted into magnetic form is the inductive side of it. Therefore, it is necessary to create a magnetic path inside the system for the magnetizing energy machine draws magnetizing component of the current. While I'm making the magnetic field in an inductive circuit on one set of coils, and then it's drawing that magnetic field on the opposite side with the secondary coils. And this would be like a transformer motor. And then it is either transforming energy, as in a pole mount transformer, or pad mount transformer, or a motor. This power is known as reactive power. So inductive power has to react to a magnetic field. Resistive power just does what it does through a complete circuit. So what is power factor? In electromagnetic energy, the power factor of the AC electrical power system is defined as the ratio of the real power absorbed by the load to the apparent power flowing in the circuit. So what we're having going on here is our entire circuit has some resistive and some inductive load. If I had a completely resistive circuit, all of the energy being used on my circuit was of a resistive load, my power factor would be excellent. And we'll see some waveforms down at the bottom. That's what we want on our entire circuit. But obviously, I'm going to have some inductive to be able to turn motors for air conditioners and fans and all that good stuff that has to have an electromagnetic field. So my circuit definitely will never be totally resistive. It's going to have some inductive load on it. Inductive, because I had to convert it to a magnetic field and then be received on another magnetic form to turn the motor, is apparent power. So the waveforms, and I'll scroll down to that, are completely different from themselves. So we're going to go to resistive first. And we talked about this before in previous classes. When my volts, you see the voltage line here, and my current are in the same phase, you'll notice on my complete peak here of voltage, I am asking for the same amount or distributing the same amount of amperage. This is the best utilization of both the voltage peak and the amperage peak in a 60 cycle waveform. On the other hand, when I have to induce voltage to a component such as a motor, for one, there's a timing thing because I have to create and receive a magnetic field. the motor at all times is going to be wanting power before my voltage can get to it, because it's having to go through the magnetic field process. So we're going to go, the blue line is voltage. My voltage is peaking here, but my motor is asking for the amperage or trying to turn its hardest here. So this is an inductive load. Conversely, or inversely, when I have too much capacitance on my circuit, my load has been satisfied back here, but my voltage is ahead of it. So voltage leading in that, voltage lagging in this. Both of these instances right here, overcapacitance and undercapacitance, are really not desired on a utility circuit. Resistive, the best utilization of our power, both volts and amps, is what's desired. So to offset that, I can take a capacitor bank on my inductive side, and when I introduce voltage into the circuit, an electrostatic charge or voltage into the circuit, I can actually make this waveform move forward a little bit. It's not drawing the amperage backwards, it's moving the voltage forward. So I can have my red line coming up more into this area and peaking closer to my voltage peak. All right. If I have too much capacitance on my circuit, I'm actually using the capacitor bank and using energy for the bank, and it's not being used sufficiently. So what I'll need to do is take that capacitor bank offline so how I can have the peak of my voltage drop back to the peak of the amperage line. Okay, in all of that, when you go out there into the world and you say you're doing an interview or you're answering questions prior to an interview for a company, I like to summarize these things that gives you all the basic information they need to know, and it does let them know that you have some good knowledge of the subject. So a summary for you. A capacitor bank is a bank of individual capacitor units, as in the pictures that I've showed you before. Those are the units. We'll go through sizing here in just a little bit. And those are the units that are in the bank themselves. And they are rated in kVAR per unit to improve system power factor due to inductive loads determined by engineers. Banks are as near as possible to inductive loads. And we talked about that previously. You'll notice in this picture that I had up here, we're at the college, and there's a lot of motor inductive load at the college because of all the air conditioning units and whatnot. Look how close this capacitor bank unit is to the load. It's as close as possible. It's right in front of the school. So this, when the motors start up in the college and I have a lot of inductive load, SCADA will send a signal to this radio. This radio will send a signal to the bank, and the vacuum switches, which are motorized, and get the signal open and close as needed. The switches do not. That's just an isolation method in case you have to work on them. And we'll get into that further. Okay, so the capacitor unit description, sizing. Depending on how much inductance I have in my circuit, I can put the appropriate size in kVAR of the unit that I want to install in the bank. So there's 100 kVAR units, 200, 300, and 400 kVAR units that you can install in a capacitor bank. There you go. That's a 100, that's a 200, that's a 300, that's a 400. I have heard cases of where they've actually had a 600 unit. That's a lot of capacitance in one location. And just to let you know, you're going to run into this out there in the world. Let's get back to this other picture right here, I believe. Nope. There you go. You'll notice that I'm looking, and by sizing, probably a 200 unit. I can't tell. They do have nameplates on the side of them if you need to identify what size kVAR they are. But I have 3 units, and we'll say they're 200 apiece. So this is a 600 kVAR capacitor bank. 3 times 2, 600 kVAR. Each individual unit is worth 200. You can get these racks and actually stack units or parallel units. So if I got a bigger rack here and I put two 200s for this phase, two 200s for this phase, and two 200s for this phase, so 400, 800, 1200, that would be a 1200 kVAR capacitor bank. There's lots of combos that can go on as far as the kVAR that you need. So if I needed, you won't mix and match sizes. You'll either use a pair of 200s or a pair of 100s, a pair of 200s, a pair of 300s, a pair of 400s. You can triple them up, but you won't make a funky, if you notice they're all staying in even numbers, you won't make like a 500 kVAR capacitor bank. They're all going to stay balanced in those situations. Okay. And they can be parallel, which we discussed before. So what do they actually do inside? Short and sweet of it, it stores and releases energy in the form of electrostatic. Well, we know from before when we talked about electrostatic field and electromagnetic field, inside there's just two plates, and the two plates are separated by a insulation. So they act essentially like a living battery. One plate charges the other plate with electrostatic energy, and that energy is released into the system. Now, realize this is happening how many times per second? 60 times per second. So I'm taking the peak voltage in electrostatic volts, and I'm reintroducing it back into the electrical system in that fashion. That's the short and sweet of it. If I was to put, let's say, a transformer up there, which is the exact opposite of a capacitor bank, and take a transformer and say I wanted to convert 7200 to 240 volts, well, that's electromagnetic. So that's actually an inductive load. This does the exact opposite. So why do we use them? Well, our electrical system is comprised of resistive and inductive loads. Resistive loads are very efficient in terms of voltage to amp consumption, and that's the one that's right in the middle right here. That's how we want our system to look all the time. But do realize people are turning on lights, turning off lights. Motors are starting and stopping on an entire feeder circuit, so it is never in this fashion at any one instance in time. It'll go lead, it'll go lag. What you do not want to happen on your system is if this lead of voltage or this lag of voltage goes way out of form. You don't want this capacitance, and this is capacitance, volts are ahead. You don't want capacitance way out here on the peak while your amps are at your lowest, and vice versa. In lagging voltage, you don't want your amperage way out here and your voltage way out here. That is the most undesirable way that you want your circuit. So you want capacitor banks to adjust and bring it back to its resistive form the best that it can. I just want to stress though that that's dynamic, that these lines are moving all the time. And of course there are times when the bank's going to come on and offline as needed. All right, so inductive loads are completely opposite. As magnetic induction needs to occur to produce power, capacitance loads offset inductive loads. It's a real good term right there to remember. So what's a capacitor bank pole configuration? Let's take a look at it so we get down to all of our material that goes on in a capacitor bank. Let's see if I got. Let's talk about the bank itself here real quick. All right, so I have my low side riser here, here, and here coming off the switch. And these are vacuum bottles. And when I say vacuum, there's exactly what I mean. There's nothing inside of them. And if I need to make or break load to the bank, it's done inside this bottle right here, and no arc occurs. So I have to have one per unit or one per phase going into the bank. You see one's over here slightly hidden, 2 and 3. Notice underneath, this is a newer unit right here. You have a manual open and close handle, Some of the older units on the bottom right here do not have this handle. They'll have a green or red flag. All right, green means open, red means closed. And go back to this one right here. So we've looked at this part, different type of vacuum switch, but it's still got the yellow handle that you bring down. Down is open, up is closed. If you notice, these are down. It's supposed to be up in this little collar area right here. So these vacuum switches are open. Okay, sorry about the phone call. All right, so for the total picture right here, we've got our stirrup hotline clamp, high side riser down to the lightning arrestor, and the lightning arrestor into the switch. We'll come over to this side. You need one per phase. Scroll up a little bit for you guys. All right, through the fuse. Low side riser goes into the vacuum switch, and then the vacuum switch goes into the capacitor bank. Capacitor banks, remember, are, if you remember in the first part of the chapter that we looked, are very volatile. And they can store huge amounts of energy, more energy than you would expect on a regular volt to amp, say 7200 volt system. They can actually store energy for a short-term period. And when they are in operation, say if these bottles were closed, it is very hard, very difficult to break load with a fuse on a switch with a stick. So to do that, one of the purposes here is to break load. All right. Second part of the vacuum switch, this is the automation part. Obviously, if I need to open and close capacitor banks through the course of the day, I'm not going to send a lineman out to open and close the switch every single day at 4 in the afternoon or 8 in the morning. This is all automated. You see the control box right here, and that control box cable is going to go down to a control panel. There you go. Our control box. This is a newer style control box, but you can essentially do all the functions that you need to as far as opening and closing the vacuum bottles with this. All right. Also, this is SCADA controlled with one-way communication. My substation can send a signal to this particular bank and open and close it by radio automatically. The dispatchers aren't even doing it. If the substation recognizes that the power factor, and you saw those waveforms before, is bad, and we have a large inductive load, it's going to send a radio signal to this control box mounted on the pole, and that control box is going to close the vacuum bottles. Vice versa. If the substation sees that the waveform there's too much capacitance on the circuit, it's going to send another signal to this box and say open. And this box is going to send a signal up to the vacuum bottles, and they are going to open up. See, this is pretty good right here. Capacitor bank, control cables coming down, actually go into this piece of conduit, down to the control box. And actually, to help reception right here, they've installed an antenna that can receive the signal. All right. And that control box has the wires in it to come up back up here and say open and close the bottles. So this is fully automated in this instance right here. Maybe you get a good description of that. When I say one-way communication, you know the substation is over here, Singleton Ridge. I'm not going to drive down the road here, but you have seen it from the field. Signal is coming from there. It receives it. It does what it's supposed to do, and we'll say close in this situation. Well, how does a substation know that the bank closed? It's still getting the readings from the circuit. So the waveform is going to come closer to the resistive normal. My voltage, my amperage won't lead as much, and the voltage is going to come more in line with the amperage. That's how it knows if it changed. Okay, and it's actually just reading power factor. When I talk about power factor, and when you hear about power factor, these three diagrams are it. All right, either a current voltage leading, or a voltage lagging situation, or a resistive circuit. All right. Both of these, if my voltage is lagging, I have a negative power factor. Excuse me. If my voltage is lagging, this one gets funny, and my amperage is leading, then I have a lagging power factor. My power factor is lagging, voltage is lagging. Okay. If my voltage is leading, then I have a positive power factor. What you want is an even power factor. So if you hear power factors, that's a good way to describe it right there is by those three diagrams. Okay, so we've gone through the pole configuration, 3 fuse switches. They're arrested cutouts, so they have a lightning arrest them. 3 vacuum bottles, the bank holder, which is the bracket, and the bank units inside. All right, SCADA monitors the substation power factor and opens and closes capacitor banks accordingly. No human intervention needed whatsoever, and it's fully automatic. If you think of this, and this is a good kind of situation to put it in, we'll use the college for an example. So and we'll use a hot summer day. So at 8 o'clock in the morning, it's typically, okay, I'm not really having to run that much air conditioning, but you get to around noon time and a lot of air conditioning units kick on. The substation is going to be seeing the power factor that is poor, and they're going to send a close signal to the bank. Well, that bank might stay closed for, let's say, about 5, 6 o'clock in the evening until the power factor becomes more a resistive circuit. When it becomes a better circuit, then the SCADA control, the substation is going to send a signal over to it, say, open back up. Because I don't want to do what? Go over to too much capacitance in my circuit. So that's where the automation falls in. Vacuum bottles break and make load in a vacuum and can be SCADA radio controlled. So we already discussed about that. So that's the overview of what they are, why we use them, and where they're located. And the where part, I've just been going back and forth to, and just remember this, as close to an inductive load as possible. The where location is, if I have a inductive load, I want my capacitor bank as close to that inductive load as possible. It's more efficient in that location. Okay. So, how do we work on a capacitor bank with SCADA control? Remember, SCADA for capacitor banks is typically one-way communication. You might find an instance where it sends a signal back to the station and confirms closed, but really that's overkill because I'm already measuring that information in the substation. I really don't need you to tell me from the bank itself and send a signal back to let me know that the capacitor bank is open or closed. All right, so how do we take one out of service? First, you're going to contact your dispatcher and obtain a capacitor work permit. First step. So obtain a capacitor work permit from dispatch. This disables the SCADA system from sending automatic opens or closes to the bank. That's definitely something that you have to do prior to working on the bank. You don't want the substation sending a close signal while you're working on it. That would be extremely bad. So it's a simple process right here. The dispatcher says disable this unit. And just like everything else we talked about before in an electrical system, just give them a pole number. I'm at pole number 1, 2, 3, 4, 5. I need a capacitor bank work permit on this unit. All that does is disable SCADA from sending signals to the bank. All right. Now he can, that's automatic side of it. He can still send signals at his discretion. Remember, the bank is still energized. We expect it to be still energized. You're going to request an open signal to be sent to the bank to open the vacuum bottle switches, confirmed by the open handle or green or red flag. Let's go back to our pictures here. Of course, I'm going to click on every single one of them until I get the right one. All right, you'll notice in this one right here, I've got the oil switches right here. Vacuum switches right here. And you can tell by looking at them, if you need to ride up there and confirm in a bucket truck, you can, but they're easily visible from the ground. The handle is down, and that is open. If the handle was up in this groove right here, it would be closed. Let's see. There is one more. Okay, another one with handles. This handle will be down, and these can be operated with an extension stick or a regular switch stick. What's not in this picture, I didn't find many on the internet because they're pretty much older. Just to let you know, they might be out there in the field. There are some that have a plunger, spring-loaded plunger on the side. You just press that in with a stick, it'll open, and it has a green or red flag on the bottom. Okay, when green, it means open, red, it means closed. Now, this is a huge reminder, gentlemen. That is not a visual open point. It's giving you an indication of an open, but these are not visual open points. The visual open point is actually inside the canister, and you're not going to take the canister apart to see it. That's why we installed switches up there. So before anything needs to be done, we'll get back to our steps. We'll go back to 2. Request open signal be sent back to the bank to open the vacuum bottle switches. Confirm open by handle or flag, green or red. Test with noisy tester or tick tracer each one of the bank cells. Now, from the previous video of Solid Underground, you know what a noisy tester is. Tick tracer is the same thing. It's just another name for it. You hold it on a wand or on a stick, move it close to the suspected part, and it's either going to give you out a high-pitched fast tone, or it's not going to give out any. It's going to give out a slow tone. The high-pitched fast tone will let you know that is still energized. Test it with a noisy tester or tick tracer first. This will confirm that your bottles are open. You're still not able to work on it yet. Stand by. If tested dead, open fuse cutouts. Well, I show a green flag. I've tested each phase in the bank, and if they did test dead, open the fuse cutouts. Well, I keep going back to the same picture. There you go. Okay, so let's go through the scenario here. Open signal sent. This handle moved down, or I have a red or green flag. I take my tick tracer up here to the bank cell. If I test this, it's still energized. I take it up to the bank cell and I test 1. It's hard to see in this picture. There's my next one. I test 2. I test 3. I'm on my noisy tester on the bank itself. All of them are de-energized. Now I know I will not be breaking load. The vacuum bottle did that for me. Now I can open my fuse cutouts. All right. Now that I have this situation, do I have a visual open point? Switch open, switch open, switch open. Yes, you do. Now you're able to start work here. If tested dead, open fuse cutouts. Number 5, and you'll notice these things in red. Wait 5 minutes. What does a capacitor do? Both a small one and one on a utility system, it holds a capacitance charge. We got to wait for that charge and those plates inside those capacitor cells to bleed off and balance off to ground. So we're going to wait 5 minutes before we do that. If you open the fuse cutouts immediately and put your grounds on, you're going to get that capacitance charge. You're going to get a spark, a pretty good one at that, and it's going to make a loud explosion. So you wait 5 minutes. After you've waited 5 minutes, ground the capacitor units for each phase. And that's as simple as you've got this going to the capacitor unit. Let's take this protective cover off, take a jumper, and go from here to the pole ground. The case is also grounded. Just take a jumper from here and go to the case if you need to. After that has been done. All right. Remember, you're not doing this by hand. This all has to be done by sticks until every phase, every unit is completely grounded. All right, perform all the maintenance that you need. All right, well, it's just plain and simple. This low side riser was burned up. So I recut it, reinstalled one, put it in. This cell was bad. So I disconnected the leads, pulled it out, put one back in, reconnected it, whatever you need to do. This is a bad vacuum switch. All right, disconnect it, unbolt it from whatever the process you need. There's multiple things you can do in here, but you perform all your maintenance that you need to. You got a visual open point, and it's been grounded. You can do whatever you need to do within the unit. Okay. Test with noise or test. All right, place it back in service. Well, you completed all your work. Let's run back to this picture here real quick. So right now, as it stands, when you have completed your work, say you replace this unit, and this is the one put back in, your vacuum switches are still open, your fuse cutouts are still open. Ensure all work complete and grounds removed. So just do a second look over to make sure everything's connected correctly and remove your grounds. All right, confirm your vacuum bottles are still in the open position. Down, down. I'd have to drive over here or the bucket or whatever and look on the other side. Down. All three switches are open. If I have flags, it should be green, green, and green. Green flags in the bottom. Close the fuse cutouts. Remember, I've got an open here, here, and here. So if I close the fuse cutouts, it's not going to be energizing the bank. It's going to be closed. I'm going to have power going down my low side riser to the vacuum bottle, and it's going to stop here because I have an open vacuum bottle. It cannot go to the bank. Move far away. This is in red. 100 feet or more if possible. As I told you before, capacitor cells, capacitor units are highly volatile and dangerous. This is why a good, if not all of your utilities have gone to SCADA control with the radio. If you'll notice right here, I'm done on my work. I'm ready to put this thing back in service. I can get way over here somewhere. Right? You definitely want to try not to be underneath it. For one, you're going to be under a fuse switch. If something goes wrong, that fuse is going to blow. It's going to come straight down. Two is, and these things are oil filled, if this capacitor itself decides to explode for any reason, it has a fault inside it or whatever, then all of this is going to happen right over the top of you. So you definitely want to be able to back away. That's what SCADA affords us. Contact dispatch and request close signal to be sent to the bank. You really don't need to be there to confirm the closed. And when they send closed, why can't I get it right the first time? When they send closed, these handles will go up. Bang, 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 all three at the same time. Or you'll hear it inside, and all of these green flags will turn to red. Well, that's all happening from the SCADA system. You don't have to be there to do that. How do you know out here in the field that it did close if you back so far away from it? Well, just like we had said before, SCADA in the substation is monitoring it. So typically, the dispatcher is going to say, well, I see a change, or I see a power factor change on all three phases. He can tell by individual phase, so it did close. You don't need to be there right at that location to do that. So you contacted the dispatch, you got the closed signal sent to the bank. If all is well, approach the bank, confirm vacuum bottle is closed. That's just a nice thing for you to do. You give it about a minute or two after it's been closed. All right. Confirm with dispatch the change in power factor. So if they have not told you, did you see a power factor change on all three phases? You call your dispatch and he's going to say, yes, I did. Good to go. And you cancel your capacitor work permit. You're finished. So you want to put this back to automatic operation. That's it, guys. That's one, the efficient way, and two, the safe way to be working on capacitor work permits. Big items here. Before grounding. And to determine if your vacuum bottles are open because you don't have a visual open point, test with a noisy tester or tick tracer, the bank cell itself. Wait 5 minutes. I've seen some guys that, yeah, I got the open signal. I've tested it, and then I'm in a hurry. I want to get the, I got to put my grounds on right away. They didn't wait, and that capacitor still had a charge on it. You've got to wait your 5 minutes. Ground the capacitor units for each phase, and when you're using SCADA, use it to its full extent. Move away, as far away as possible from the bank on a close. All right, more safety here, gentlemen. Typically, if you're working on this capacitor bank, what's going to happen with the industry right here, I know I've spoken with Professor Vermlin, and I know we practice this ourselves. I didn't include it in the previous steps. If we got these open switches right here, and we're working on in this area right here, by legality, as far as approach distances, we're okay as being, our distance from the primary and energized primary. Remember, the high side riser to the top of the switch is still energized, but we're doing our work down in here, so we have enough clearance. All right. Some of your utilities are going to tell you, and it's going to be an instruction, well, you've got an open point, you've got a de-energized bank, go ahead and take the high side risers off. That'll just give you that much more clearance. All right. That's what Santee Cooper says to do. That's what Duke Energy says to do. And it's a very good practice. So just go ahead and take these off. They're not in use. You've got an open switch. And when you get done with your work, you can put these back on before you start closing the bank or putting the bank back in service. Okay. Remember, at all times, if you need to go above the switches into primary approach distances, a hotline work permit is required. I've fixed multiple banks, and the guys in my crews have repaired and done maintenance on multiple banks where they have not had to have a hotline work permit. But during the work, say they notice this switch is bad, or they got a bad fuse barrel or bad connection. Well, now I've got to get up into this area that I'm going to put my rubber goods and everything on it, just like I would before. I'll take the riser off, but you are in hotline work permit area. Once you get above the bottoms of these switches, you are in hotline work permit areas. So obtain that hotline work permit if you need it. If you got the hotline work permit while you were doing your work, it must be canceled before the switches are closed. Step 3. A good dispatcher is going to tell you, look, we're getting ready to go into the process of closing or putting this bank in service. You've got a hotline work permit. And if you remember back from the substation and the breaker and the protective devices, if he closes this bank and there's a fault, you're going to get an instantaneous operation and it's going to lock the breaker out. We don't want that to happen. If we close this fuse and we get a fault for any reason, or if they close it by SCADA, the bank, and you have we want the fuse to blow. And we discussed before on our tap lines and transformers, we use a KS fuse. This capacitor banks typically use a very fast fuse inside of them to blow so the breaker won't operate. So if you obtained a hotline work permit, cancel it before you re-energize the switches or the bank. How do you like that dyslexia right there? All right, what's a fixed static capacitor bank? A bank that stays closed 24/7, 365, sometimes not controlled by SCADA. So let's go back to our map here. You won't find these very abundant, but they are out there in the world. Just load up for just a second. And they are unique situations. So where am I? Just scroll out here a little bit. This is Seaboard. Here's 501. This is Highway 17. Broadway at the beach. And what I'm going to zoom in on here is 21st Avenue Substation. That's the substation right there. And if you'll notice, coming out of the substation, I know it might be a little bit difficult to see in your video right here. I have a feeder coming out to here, coming up to this pole, and I've got a capacitor bank on it. This, gentlemen, is a fixed capacitor bank. I know that from working in this area right here. So it stays on 24 hours a day, 7 days a week, 365 days a year. Fixed or static bank. Well, why would you have a fixed or static bank? I'll go ahead and completely go down the circuit. And where do we arrive? Grand Strand Water and Sewer Treatment Plant. Grand Strand Water and Sewer Treatment runs 24/7, 365 days a year, and has a humongous motor load to pump. Well, you get it. You know what it's pumping. Both sewer water and reclaimed water in this area. So that's a good description and good overview. Substation, fixed bank, close to the load as I could get it right here. These are, and the reason why this is a wood pole and these are steel, I couldn't mount it on a steel pole. And there I have my 3-phase inductive load that stays on all the time. So I went ahead and put a bank in there. Not I, but an engineer requested a bank be put in here that stayed on 24 hours a day, 7 days a week, 365 days a year. Okay, all vacuum bottle opens or closes are done manually at the control box. So when I say sometimes not SCADA controlled, you're actually going to have to go up to the control panel in these cases. And actually, you see a trip and a close. There's some other different settings that are going on in here, but the trip and close is the majority of what you're going to use all the time. And to be able to open it, you're going to have to trip it open. Tripping open, I've got no problem with. You can be right at the control panel to do that as you're actually de-energizing something. The close is where you need to be safe and watch what you're doing here. So, closes can be done with a stick from a distance. Well, kind of surprisingly, they do make an attachment for switches, and sometimes you can just use the actual end of the switch. If you don't want to get right directly underneath it, right here, you can take a stick and stand in this location over here and put the stick out and actually press the close button from this distance. So that's another safe way to get away from the bottom of the pole. The fuse is going to eject right down here, right in this area. You can get way over in this area, out from underneath the bank, and press that close button. Sorry. Oh, my computer's getting slow. You press that close button with the end of a stick. A lot of your companies are getting this to be in the SCADA realm, and you really won't find that many situations where you're going to be finding a capacitor bank that's not SCADA controlled, but I did want to include it. There are some safety measures you can take to get away from a bank. All right, the capacitor units themselves. $100, $200, $300, and $400 right here. All right. And like I said, even if you got the $300, you're going to pair it up to make it a $600. In these units, and this is kind of not a good picture right here, just to let you know, gentlemen. I'll go back to my document. At all times during transport or storage, capacitor unit terminals must be shorted. So what I'll need to do, and it doesn't matter what size or type of wire that you use for this temporary time, is get a jumper or a piece of copper or a piece of wire with 2 hotline clamps on it and put it terminal to terminal. That shorts the capacitor out, so it cannot build up a charge. I have seen in situations where these have been in storage under lights, especially for fluorescent lights, and fluorescent lights will charge the unit. And people have made contact and it has snapped them pretty hard. Think also too, if you're transporting this on your truck or fleet or the truck that brought it to you, and these are not shorted, you can get wind static. So the wind blowing up against these can actually charge the unit and have an electrical charge inside the capacitor cells. They must be shorted at all times until you get ready to install them in place. If not shorted, they must be treated as energized and shorted. All PPE plus sticks and rubber gloves. So I'm not just going to go up here and think, well, nothing's on it. I'm just going to go ahead and short it out with my regular gear. You got to treat this as energized. So you're going to have all your hard hat, your rubber gloves, your boots, your fire retardant clothing, your safety glasses. Everything that you need to do as if this was an energized situation, and take the jumper and put it on both terminals with a shotgun stick. Okay, the capacitor units store electrostatic energy from static and electromagnetic sources, even lights. So that's the reason why that you need to make sure they're shorted, and if they're not shorted, treat them as if they're energized until they are shorted. All right, one last piece right here, and I'll just go ahead and stick it down to the bottom. Remember, when the bank, let's get this corrected, when the bank opens, closes for both switches and VACU vacuum, yeah, I got it right, bottles, hearing protection, it is required. Okay, so even down here at the bottom of the pole in these situations where we're working on something like this, or if you're up in the bucket with a stick, or if you're using an extension stick, the potential of a fuse blowing is there. So at all times, even if you're on the ground, have your hearing protection on in case one of those fuses decides to blow. If you remember in the on the close process when we have SCADA, we're actually able to move over here somewhere and get away while those vacuum bottles close and close on the bank. Have your hearing protection on even over here too. Okay, if something goes wrong here and that fuse blows, you've got your hearing protection on. Gentlemen, that pretty much covers it for the day. I'm going to post this in the D2L site. I'll post the video in the D2L site. You will have quiz questions on it. I did find another video that gave a good description of power factor and kVARs, and I'll include that too. But as of now, have a good day and appreciate all your hard work.